Hi there. So in this video, I'm going to be talking about a very important concept in marketing mix modeling, and that is called the Bayesian approach. So there's been a lot of buzz lately around Meridian, which is the latest marketing mix modeling, free and open source solution from Google. Um, and there's also been a lot of talk about it being Bayesian. So that's exactly the topic of today's video. I want to discuss what exactly does it mean for an MMM, for a marketing mix model, to be Bayesian. So this is going to be a little mathematical, but the whole point about this video is to give you an introduction, no matter what your background is, as to what really Bayesian means. And this is not going to be just limited to the context of Meridian, because there are a lot of other marketing mix models out there which are using the Bayesian approach, and there are also other statistical and digital, web analytics tests that are carried out, experiments, A/B tests, that sort of thing, which are using the Bayesian approach. So this is going to be relevant to all of those use cases. But in front of you right now, you can see the Python notebook, which has actually been supplied, the demo notebook that has been supplied by Google in its Meridian documentation. And you can see that under configure model, they have the section here for assigning the priors. They have the section for the priors, and then um, a particular distribution, the prior distribution. So this is that part, which is the most hyped about. How do you assign priors? What does priors really mean? Is it a good thing? Is it a bad thing? What are its advantages? What are its demerits? So we're going to go into some of those. We'll not be obviously covering everything. It's impossible. Bayesian statistics is a huge subject. We're only going to talk about parts of it, but it should be a good introduction. So first things first, I'm going to be using a different notebook. I just gave you a snapshot of what Meridian's notebook, what Meridian's demo code actually contains. But we're going to be doing something different. We're going to follow a textbook which is called, some excerpts from the textbook, which is very good. I mean, I don't know if it really is a textbook it can be called, but it's an online really good book on statistics, which is called Statistical Thinking for the 21st Century. Russell Poldrack, I think from Stanford, has penned it, and it's completely open source and free to access. So this is where I got the concepts. It also has a Python companion, so definitely look into that. So I've taken the problems and the code from there, and this has really discussed Bayesian statistics very well. So uh, Bayesian statistics is actually based on the theorem of Bayes. So this is something that we had all studied in school. This is the basic theorem which has four components to it. So probability of hypothesis given data, which is the posterior distribution. This is what we are trying to get. Okay, the posterior value of the distribution. Then there's a probability of data given the hypothesis. This is the likelihood. Um, and this is probability of hypothesis, which is the prior. This is the prior that we are assigning. So the prior that you just saw within Meridian's notebook, and the prior that we are all hearing about in the context of Bayesian statistics, this is that prior, basically. And then there is, probability of data, which is basically called the marginal likelihood in the context of Bayesian statistics. So these are the most important components of the Bayes theorem, and we're going to look at each one of them and their relevance. So in this problem, this is basically a drug administering test, and it's also going to test the efficacy of this drug. So there are several people who are going to be administered this drug, will be administered this drug, and then it will be checked whether or not they are responding positively or favorably to that drug, whether the disease is getting treated. So you can see that there are two important concepts that are introduced here, sensitivity and specificity. So if you're not already aware of them, these two are very fundamental uh, criteria to understand, um, classification. So for instance, if you just jump into this part here, so sensitivity, whether or not something has been classified correctly. So for instance, when it detects a condition when it is truly present. So this is given by this conditional probability. So this is called a conditional probability to those who are uninitiated. Probability of testing positive when the condition is actually present. So suppose a patient does really have the disease, and then the test is actually truly and properly classifying them as having the disease. So this is called sensitivity, and that percentage has been given as 90%. So this has been, sort of taken as a near mark, as a benchmark. then the specificity is the true negative rate. So this is correctly pointing out the negative. So somebody has tested is negative when the condition is genuinely absent. So generally in these cases, the specificity is always higher, as you can see, 99%, and that's because you do not want a false positive. You do not want someone to be assigned or classified as a diseased person or as having the disease when they're not, because then they will be, being given drugs which they should not be getting. Of course, the other side is also important, where you don't get the treatment even though you are actually positive, but generally specificities are given a higher rate. But again, this is a matter of judgment. This is just, for example, just to get you started with Bayesian. The prior has been taken as 74, 0.074 rather. And as you can understand, this basically means that this is a prior understanding of what could be the proportion of people who actually are going to test, who are going to be properly evaluated or classified. So the likelihood in this case is equal to the sensitivity. So we already saw the likelihood, the likelihood from the equation, the Bayes theorem equation. In this case, it is equal to the sensitivity, and that makes sense. What is the most likely data given the hypothesis? So that's the likelihood, what the data is going to show. That likelihood is basically taken as the sensitivity. And then you have the definition of marginal likelihood. So the marginal likelihood is sensitivity into prior into plus 1 minus specificity into 1 minus prior. So this is actually coming from another couple of concepts which we'll go through quickly. One is called the law of total probability, another is joint probability using conditional probabilities. So first, this theorem is very, very common and popular. It's probably the first thing that you learn when you learn probability in high school. Probability of A of an event A is probability of event A intersection B plus probability of A intersection B complement. And so this basically means that probability of A occurs, but B does not. So this can now be actually changed into this form using the conditional probability concept, where we use this concept first. Probability of A intersection B is nothing but probability of A given B, the conditional probability into probability of B. This now is changed into probability of A intersection B complement. So we just take the complements and you can see that this formation comes about. And then we just replace this part here. This part exists here. You can see this is the right part on this side, and this part is simply this part here. So just replace these two from these two equations and you get this formula. And this formula is exactly the form that you see here, sensitivity into prior plus 1 minus specificity into 1 minus prior, because sensitivity, as you know, is likelihood, and the rest just follows from here. For instance, prior here is the B, and the rest just follows. So that is how it is progressing. And then posterior is taken from the Bayes theorem formula that we just saw, likelihood into prior by marginal likelihood. Let's see that again. See, likelihood into prior divided by marginal likelihood. And now what we get once we print this is simple Python code, is what is called a point estimate. So this is 1 point estimate for the posterior value. But what we really want is a distribution. That is the most important thing. That's where we are trying to get at. So next we are going to load some libraries, NumPy, Pandas, SciPy, Stats, Matplotlib. This is for plotting. This is for carrying out statistical calculations. You'll see in this little bit of code, it's not there. It's going to be used later for something called a binomial distribution. We're going to come to that later. So now, for the purposes of this next exercise, we are moving step by step. So that was a point estimate for the posterior. Now we're going to create a posterior function. So as you can see, this posterior function has been created here. Once again, likelihood is sensitivity. Marginal likelihood has the same definition. Posterior has again the same definition. Everything is same. So why is it a function? It's returning the value of posterior. So it should give a point estimate? No. So in this case, it has got a range of values. As you can see, it varies from 0.001 to 0.05 to 0.5 in the steps of 0.001. So this is a discrete distribution. And you can see that the prior value earlier was a single point value. This time it is a range. And once we give the prior values and we compute the posterior values from there, so we just give these arguments now to this function. And you can see this is what comes about. So we have a range of prior values, and posterior values are also distributed in this fashion. And it kind of saturates close to the value of 1, okay, as the priors are increasing. So that is how it is working. So this, by the way, again, is just a discrete value and a discrete distribution, and Once again, not any specific kind of distribution. This is just being derived from prior values. Okay. So now what we're going to see is this one where we'll see that it is another, so basically the values have now changed. So we have number of responders is 64, and now the number of people who were tested by 100 is 100. So now we're going to go to a case where we will have a uniform distribution of the prior, where the prior value is uniformly changing. And this time we're going to have the binomial likelihood for the observed, for the observed data. So that's probability of the data given the hypothesis. Remember, that is the definition of likelihood. So if we are going to look at the previous thing here, so the likelihood was simply calculated as equal to sensitivity. So this is what is changing this time. This is the this is where we are first time jumping into different distributions. So this is a very important part. So assigning priors actually depends on these things, okay? Because there will be several things where it will be important to decide what kind of distribution that you should be choosing. So if it's a prior distribution, if it's a binomial distribution or it's a beta distribution, there's so many kinds of distributions, and by distributions we really mean probability distributions, where the the y-axis or the fx value, basically it measures the probability of each point across the distribution, and depending on whether or not it's a discrete or continuous distribution, we'll get the corresponding probabilities and the corresponding curve for that. So this time we're creating a data frame called VSDF, and it's consisting of this column here. So we are creating this column proportion, which will simply have the values. So this is basically, this proportion is going to feed into the binomial distribution. This is going to be its x value. Okay, let's actually look at quickly what the binomial distribution really looks like. So this is what the binomial distribution looks like. So if I just were to quickly go through what's happening previously, so the likelihood function represents the probability of observing the given data, assuming a particular proportion theta. Okay, so that's your hypothesis. So this is the binomial probability mass function. It's probability mass function because it's a discrete distribution, remember? And this is the normal regular binomial theorem, or rather the binomial distribution formula. So n, you have two major things which are varying. So n our parameters, rather, your varying thing is your proportion, and you have n equal to 100 and k equal to 64 in this case. So basically the total number of trials and the number of successes. So these are the two things which vary, and there are only two possible outcomes in case of binomial distribution, whether it is a success or a failure. Right, so that's what we're dealing with. So these are the important questions when it comes to choosing distributions. Why choose a certain distribution? So for instance, why binomial theorem was chosen as the likelihood distribution in this case? These are very important questions, and these are actually more crucial questions when you're talking about things like MMM. And this was chosen, as you can understand, when you're having a drug trial sort of a thing. It's going to be yes or no, right? Either it is going to be false. I mean, either it will be true or positive, or false or positive. Right, true or negative, true or false, anyway. So so that's how it's happening. So SciPy stats binom EMF. So that's the way you invoke this function for the binomial theorem, for the binomial distribution, and then you have the responders tested and finding the proportions. So that's your x value, right? So you have the x value, which is basically working as your theta here. And so then we move on to the prior. So in this case, we'll actually have a completely constant same prior for all the values. Okay, and that's why you see when we are plotting the prior finally, you see that is a complete straight line here, and you see that it's a certain value. So what's that value? That value, as you can see here, is, as it's being created, a column is created for the prior. It's nothing but 1 upon the number of rows, or the total number of. So this gives the number of rows in the data frame, and that's nothing but just the total number of tests that have been carried out. So that's in this case it's 101, as you would remember, right? So 100 were total tested, and since it varied from 0 to 100, it's actually 101, right? So there you go, a total probability of 1 by 101. So that's constant prior. Now, it's of course, and this thing actually constitutes what's called a uniform distribution. Okay. It's 1 divided by b minus a. So it's a uniform distribution and all the values are equally likely. Now, there's going to be another discussion that we'll have shortly. When you have such a distribution, typically when you don't have too much information or you don't want to feed too much information because you don't think that you have enough information in order for the algorithm to pick up and act correctly, then what you often do is choose something like like a uniform distribution. This is typically called a weak prior or an uninformed prior. Okay, where you have kind of plateaus or this is like a constant value. So it's not adding anything different, right? So there's no variability. It doesn't have any kind of dependence on anything else. It's just constant on its own. So is that really useful as a prior? Suppose you were to do that. Suppose you were to say, that there's a constant value that I'm providing. It doesn't matter. The prior is irrespective of everything else. So that's not very useful. Or suppose you say that it's going to have like a uniform value always. So that's not very useful either, right? So in that case, what happens is sometimes it can be deliberate, like I said. So sometimes that can be a starting point. That's exactly what's going to happen in this case. So it's a good thing to start from there when you don't have too much knowledge. So what Bayesian theory, and this is the power of Bayesian statistics or Bayesian approach, I should say, is that it's going to use the knowledge of the previous analysis. So for instance, this is one iteration where you're assigning a very uninformed or a weakly informed prior. But later on, once you have the posterior distribution generated from it, as we'll see, we'll actually use those values as the next priors. So that is how iteratively it carries on its tasks. In this case, we are doing this manually. This can also go on internally within MMM models as a recursive process. So then we actually move on to marginal likelihood, and then this is defined as the likelihood and the prior, the multiplication of that, and the summation over all of that. So it's called sum product. This is what it looks like, essentially what's going on, because the probability of data is nothing but the probability of data given theta, overall values of theta, and then you have multiplied by the probability of theta. So in this case, there is a normalizing factor that's been taken in this problem. So therefore, what it means that it's going to sum up to 1. Okay, the entire marginal likelihood. So this is a discrete distribution, remember, which is why a summation is being taken, but it could have been an integral also, right? An integral, definite integral with finite values, or finite range of values for theta, the proportion when it's a continuous data. So now it's a question of computing the posterior, and that's how we compute the posterior. We have the posterior as a column, then we use likelihood and prior and divided by my marginal likelihood. That's the regular Bayes theorem definition. And then we finally move on to the plotting. So we are keeping the labels as the different things here, likelihood label and posterior, likelihood prior and posterior, sorry. And then we are obviously having the proportion in the x-axis in each of the cases. Okay, so this is theta. And as you can see, what is the probability of different values of theta when it comes to the likelihood of prior and posterior? Now see, there are actually 3 lines here. So you see that there's a dashed black line, there's a blue line, and these two are almost overlapping one another. And this overlapping functionality is where the real problem lies. So in this case, it's not really a problem, but it's a starting point, as I already said. So the likelihood and the posterior are absolutely on top of one another. And that's precisely because the prior is uninformed. Okay. If it were weakly informed, it would be close. It would not be overlapping so much. So what you really want is your posterior to actually be also informative, in the sense that it's going to give you a good idea of how it's going to vary. But if it only starts with, if it's only like probability, it's equal to the probability of the data given the hypothesis, then it makes no sense, right? So if you look at this formula here, so where the prior is uninformative, so we are talking about the probability of the probability of the posterior distribution, which is the probability of the hypothesis given data. So if this prior value stops being very meaningful, then what happens? It's a constant value. Then it just depends on these two things, right? With the probability of the data given the hypothesis, which is your likelihood, and then upon the marginal likelihood value. So in this case, the marginal likelihood value was summing up to 1, remember? That's how it was taken. So that's why these two overlap with one another. That's a simple mathematical understanding. This is a constant, and this is being divided by 1, because that's how the normalization is being done. So they are on top of each other. So see what description has been given here. The above shows that the posterior is close to the likelihood. They're really on top of each other, not just close, in the presence of weakly informed or uninformed prior, like uniform distribution. Also note that the standard uniform distribution is a special case of the beta distribution. Okay, when beta is, or alpha is equal to beta is equal to 1, so by rule of conjugacy, the posterior distribution is also a beta distribution. So there's something called a conjugate priors. So suppose the likelihood distribution has been chosen as binomial, and then for the priors, the conjugate, for the prior distribution, the conjugate prior would be a beta. Okay, and then you would have also the outcome, the posterior distribution as beta as well. That's how it works. So it essentially means that for a pair of distributions for likelihood and prior, if the output is in the same family of distributions, then it becomes a sort of a conjugate prior. That's how it's defined. So that's why in this case, the uniform distribution is actually a special case. Okay, for the values of its parameters, alpha and beta, it's beta gamma, but it's usually alpha and beta. If these become 1, then you get a uniform distribution. And in that, which means therefore that it's a beta distribution in its prior, this binomial distribution is likelihood. So therefore the posterior distribution is also going to be beta. So that's the definition of conjugacy. We can take those up later on. Conjugacy is a relatively bigger concept, but in this case, so conjugate price is one way to decide the nature of the posterior distribution. There are other ways we can we can actually have people we can actually have methods, sorry, the nature of the distribution in other ways also. So for instance, the Bayesian updating can happen through MCMC algorithms, for instance. So we're going to come to that. We're going to discuss that in later videos. But in this method, what we're going to choose is the method of using the manual method. So we are simply going to take the posterior values as the priors for the next iteration. And in this case, we simply have larger number of samples. Okay, so the number of tested has increased. The number of responders has also increased. From out of 1,000, there are 312, as you can see. So in this data frame now, we are simply renaming the columns. As you can see, we are renaming the posterior one to the prior for the new data frame. And then we are going to compute the binomial likelihood of each observed data and the possible value of proportion. Okay, so that's basically what we are doing. It's the same binomial approach that we did previously. The same approach. The marginal likelihood is the sum of product of likelihood and prior, and the same way we are calculating the posterior distribution from the posterior distribution from the Bayes theorem formula. And then we go to the plotting, and that's it. So in this case, as you see, the only change that we have done from last time is to actually take the posterior values as the priors for this iteration. And you'll see the most interesting thing here is that since samples have increased, which means that we have greater confidence. And therefore, what's happening is that you'll see that the observed study, which is 0.64, in the first case, this is the one. And this was the prior from, this is the prior for the second iteration, right? The second study. And this time we are taking that as a posterior. The likelihood is the blue dotted line. And the posterior is actually this black dotted curve here. So you can see that the posterior distribution, the outcome of the situation, is actually much closer to this blue dotted line, which is the observation of the second study, because the number of samples is greater. So we have put more weightage to this case, clearly. That's how it's worked, instead of the red one, which is much further away from the posterior distribution. So this is trying to show the relationship between the data and the posterior distribution, because so far in the previous curve we were looking at likelihood prior and posterior, but we also just wanted to look at how it compares to the data. And the data obviously is a specific proportion. So we are talking about the proportion here when it comes to the data, and that's how it is linked to the observed data. So this was the initial introduction that I wanted to give. And there are some other concepts here, very important concept. Let me just quickly go to this document if I left out anything or not really. So yeah, so this process that we just discussed, this was a relatively manual one, where we are just using where we are just evaluating or estimating the posterior distribution from the Bayes theorem directly. But that's just direct updating. Bayesian updating can be done in so many other ways. So you'll see that there are so this is the key takeaway. So the likelihood integration that I was just talking about, this formula here has p data at the denominator, right? So this is the formula for p data. In a discrete distribution, it's going to be a summation. In case of continuous distribution, it's going to be an integral. So this this is going to change if this is only for exact Bayesian updating. This is the method, but it can be avoided. Sometimes what happens is that integration becomes very difficult. Okay, so that's one of the hardest things. So the marginal likelihood integration, that problem literally gets stuck. So that's why if it becomes too mathematically complex, it's often useful to use conjugate priors concept. That's what I said just a while back, that sometimes you can have conjugate priors where if you choose a certain kind of distribution in likelihood, say binomial, then your conjugate prior distribution will be a beta distribution, because then the posterior distribution you already know. So the whole point here is to understand the nature of the posterior distribution. And I may have missed a point. How do you understand the nature of a distribution? You understand it solely through data science techniques by figuring out their parameters. Okay, so parameters define your distributions. So that is what conjugate priors can do, right? Because it's going to, you already know what the conjugate prior is going to be. So for instance, this is that example. You can read this definition here that I just said, that the posterior distribution follows the same model family as the prior. That's when it's called a conjugate prior. So if you can read up on the internet. So I've just I'm going to be sharing this resource as well with you. So there are great books like this. There are just so many good material out there. Here's where I took the definition from, and example of conjugate prior I just said, and the beta distribution. Okay, so that's a probability of success which is bounded between 0 and 1. So this is the example. So if it's a beta prior, if it's a binomial likelihood distribution, look at the parameters. This is a and b, this is n and theta, and look at the posterior. This is entirely defined in terms of a, b, and a and b, right, and n. So that's how n is the number of trials, remember, and theta is your probability of success. So that is exactly how it works. So this is the generalized version of it. This is a specific example that's been given here. This, by the way, I've taken from another note that was released by MIT, so you can just take a look at that. I can share it if you want. So this is, but yeah, there are plenty of sources. So binomial distribution, beta distribution, these are conjugate priors because the outcome is going to be the posterior, that is not the outcome really, is going to be having these parameters. So distribution, as I said, the parameters is most important, because you can say it is because you can talk about the parameters. You already know what the parameters is going to be, is why you would choose the choose this particular approach in the first place. So yeah, I mean, I got a very bad cold, but yeah, I just decided to record this video anyway. But this is the whole idea. I hope I'm not missing out anything. Yeah. So the other thing is, like I was saying, conjugate priors is just one of the other approaches for Bayesian updating. MCMC is the other one, and there are some other ones like variation inference, approximate Bayesian computation. It's a huge subject. So the MCMC is the one that actually is getting, getting used at the back end of Meridian's model. So if I jump back into the Meridian notebook once more, let's see. Okay, where are you? MCMC. So there you go. It says that Meridian uses the Bayesian framework and the Markov chain Monte Carlo algorithms. And you can see that it's actually there within the model spec. So that's how it's actually going to do its bit. It's being programmed internally. That's how it works. So this sampling here, as you can see, this is the whole point of obtaining samples from the prior and the posterior distributions of the model parameters. This is the whole process of MCMC. Okay, and this is the whole new thing. It's its own way. So instead of computing the posterior directly, it samples from it using a stochastic process. Okay, stochastic means randomized. It allows us to approximate the distribution by drawing many samples. So it's nothing but that. It just uses a simulation process. We're going to have very detailed discussions on MCMC. This itself is a huge discussion itself. And there are some common ways of doing that. There's Metropolis, the sampling process itself can vary. So there's Metropolis Hastings algorithm, this Gibbs algorithm sampling. So yeah, my battery is about to die. I hope you have enjoyed this video. This is the basic introduction that I wanted to give, and I will soon come back with more, maybe even manual runs and walkthroughs of the model itself using Python, and more aspects about Bayesian statistics as well, like Monte Carlo Markov chain. So yeah, looking forward to that. But till then, goodbye from me. If you have any questions or any suggestions, just do leave them in the comments. Thanks for watching.